In part B then, we have a particle moving with a non-zero velocity along the polar curve given by r is equal to 3 plus 2 cosine theta. That's the Lima sign. And obviously it has a position of x of t, y of t at any time t, with theta being 0 when time t is equal to 0. So basically it's moving along the curve so that at time t equals 0 it starts with theta equals 0. Then as time goes on, the angle changes and the point is moving through the curve, as you can see. And so because the particle is moving along the curve, it has a rate of change to its motion, etc. And what we're told about this is that the particle moves along the curve so that dr dt, or its rate of change of radius with respect to time, is equal to dr d theta, the rate of change of radius with respect to theta. And dr d theta, of course, is easier to find because r is a function of theta, and we could easily differentiate that with respect to time, with respect to theta. In order to differentiate that with respect to time, then we would have to convert all of these things into time. But we do know that because dr d theta and dr dt are the same, we're just going to be able to use dr d theta. And what we're trying to do is to find dr dt at theta equals pi over 3. So we're looking for dr dt, but dr dt is equal to dr d theta, and that is just the derivative with respect to theta of 3 plus 2 cosine theta, which simply turns out to be negative 2 sine theta. And at theta is equal to pi over 3, that equals negative 2 times root 3 over 2, since sine of pi over 3 is root 3 over 2, which leaves us negative root 3. And then we're asked to interpret that answer in terms of the motion of the particle. Well, if the rate of change of radius with respect to time is negative, then that means that the particle is moving in, the radius is shrinking, and the particle is moving in toward the origin when theta is equal to pi over 3, or time t is equal to pi over 3. So the particle is moving in toward the origin at a rate of square root of 3 units per unit of time. We'll go on to part C here. Well, part C is similar but slightly different than part B. In part B we were looking for the value of dr dt, and here we're looking for the value of dy dt, where dy dt is equal to dy d theta. And we don't have any y's in here, so we're going to have to go back to our definition to convert between polar and Cartesian coordinates. And since y is equal to r sine theta, and our r in this case is 3 plus 2 cosine theta, we now have y is equal to 3 plus 2 cosine theta quantity times sine theta, which is 3 sine theta plus 2 sine theta cosine theta, and that 2 sine theta cosine theta can be rewritten as the sine of 2 theta. So now we're looking for dy dt, which is equal to dy d theta. And so d d theta is 3 sine theta plus sine of 2 theta. And finding the derivative of that, we get 3 cosine theta plus 2 cosine 2 theta. We just need to plug in theta is equal to pi over 3. Cosine of pi over 3 is 1/2. Then cosine of 2 times pi over 3, which would be cosine of 2 pi over 3, is equal to negative 1/2. And so we get 3/2 minus 2/2 is equal to 1/2 would be the final answer there. And we're also asked to interpret that in terms of the motion of the particle. Well, if dy dt is 1/2, that means that as time is progressing, the y-coordinate of the particle is moving away from the origin, or away from the x-axis. Y is becoming more positive as time is progressing at that instant.